Welcome back, dear friends of Biomed and Physics. Today I decided to go international, presenting in English my Journal Club of Nuclear and Subnuclear Astrophysics carried out for the University of Trieste, over which, if you are interested, I leave you the PDF description. We will deal with the ultra high energy neutrino detected by KM3-net, the deep sea neutrino, a telescope at a depth of approximately 3,450 meters in the Mediterranean Sea. Let's start. This is a Python simulation, a part of whose code you can read on the side detailed about this event. Look it. Okay, dear friends, the goal of this journal club is to do an investigation into the origin of ultra-high energy neutrino KM3-230213A, which I'll call KM3 for simplicity's sake. Neutrinos are unique and elusive cosmic messengers, the most mysterious particles of the Standard Model, often treated as ghostly chameleons due to their electrical neutrality, weak interactivity, given their belonging to the leptonic subclass of fermions, their invisibility to magnetic deflections or absorption processes from the interstellar medium, and furthermore, their extreme lightness, weighing less than 0.8 millionths of a billionth of billionth of a billionth of a gram, about 8 by 10 to the power of minus 37 kilograms, corresponding to 0.45 electron volt per c squared. The neutrino detected by KPM3-net is the most energetic ever observed, with an energy of 220 PeV, ranging from 72 PeV to 2.6 x electron volt at the 90% confidence level, and falling in the ultra high energy region greater than or equal to 50 PeV, surpassing prior observations by Ice-Cube Neutrino Observatory by one order of magnitude. Before Cap M3, the most energetic reported up to was an 6.005 less or more 0.72 PeV electron antineutrino and a muon neutrino above 10 PeV from the observation of a 4.4 PeV muon per 110 million events triggered by HARCA. So, knowing first the arrival direction and kilometric cruise of the event, which we will return to. Two, the spectral shape of atmospheric neutrinos, which drops steeply and abruptly at higher energies, having an higher density at lower energies of about of the order of TeV than that of cosmic ones, which should become dominant at energies above 100 TeV. I'll just throw out a first clue, dear friends. Simplistically, assuming a steady diffuse neutrino flux isotropically expanded into 4 pi solid angle, their expected flux of about 1 bar 5 by 10 to the power minus 5 events per year makes the scenario of cosmic rays interactions with Earth's atmosphere highly unlikely. So we will investigate on the broad range of potential candidate sources, steady or transient, cosmogenic or galactic origin. Let's make a very brief brush stroke as a spoiler. Could Cap M3-net have been produced within the Milky Way as an effect of astrophysical catalysis from gas targets or cosmic rays collisions? or it's with extremely high probability of cosmic origin, from the bowels of which universal dragon was it spat out in the wide zoological range of sources. For example, active galactic nuclei, or so-called AGN, supernova remnants, star-forming regions, or gamma-ray bursts. First, let's place it into spatial geography. Its position was determined to be with a right ascension of about 94.3 degree and a declination of minus 7.8 degree in the 2000th year of Julian calendar, with containment rate of 68% equal to 1.5 degree and 99% equal to 3 degree. The corresponding galactic coordinates are latitude of about 216.1 degree and a longitude of minus 11.1. Therefore, the event occurred far away from the galactic center and around 11 degree offset from the galactic plane. Using a multi-messenger approach for detecting cosmic accelerators, let's count gamma ray bursts and cosmic rays, but they are both unexplored at highest energies due to deep space opacity. So, gamma rays with energies greater than or equal to few TeV interact with low energy photons of the extragalactic background light, so-called EBL, or cosmic microwave background, so-called CMB, resulting in an electron-positron pair production or inverse Compton, which severely attenuates their propagation over cosmological distances. On the other hand, cosmic rays, subatomic particles at extremely high energies of the order of X electron volt, greater than 10 to the power of 18 electron volts, violently hardened at ultra-relativistic speeds by monstrous cosmic accelerators, suffer energy losses and photodisintegration through interactions with ambient matter or photon fields, triggering hadronic processes and resulting in a mean free path smaller than a few gigaparsec. At the lower energies, charged nuclei are also deflected by the ambient magnetic fields, which further impedes the identification of their sources. Neutrino instead interact only weakly with matter and radiation, allowing them to travel virtually unimpeded over cosmological distances. So neutrinos are invaluable proofs of the most remote and densest regions of the universe not undergoing absorption or scattering processes. Look this perfect. This globe with a giant central question mark, what you see is now empty, but we will little by little fill it with the suspected sources that we will study. Let's pass and let's move on to the must essay I like to explain. This is an observation of an ultra high energy cosmic neutrino with kappa M3 net. This is the review article with its link that I could leave you on the description of this video. Let's pass to the abstract. Okay, the Mediterranean telescope KM3-net detected near horizontally and along an extraordinary route a moon with an estimated energy of 120 PeV, in contrast to the steep falls in neutrinos energy spectrum revealed so far, suggesting it could be the first cosmogenic one. All flowers of neutrino interactions produce high energy and long-lived moons called tracks, which, after having produced electromagnetic and hadronic cascades, so-called showers or Cherenkov radiation, lose energy mainly because of stochastic radiative processes such as Bremsstrahlung, per production or photonuclear reactions on average per unit path length in proportion to starting energy. Despite this stochastic energy loss, moons keep its strong neutrality and transparency to absorptive damping and resistance to spectral matter opacity. For this reason, the recorded time of arrival and time over threshold of the signals on the photomultipliers denoted as its are used to reconstruct the moon direction and energy. This is a quick illustration of a Cherenkov effect produced in the muon decay from a neutrino. It consists of an intense electromagnetic emission from polarized molecules of a dense medium triggered by a charged particle moving with a speed greater than the phase 1 of light, which is in turn reduced in the medium compared to a vacuum, generating a brilliant and spectacular wave cone, whose beam expands with an angle theta whose cosine equals the reciprocal of the product of the refractive index and the Lorentz speed factor, which is equal to the ratio of the muon's speed and that of light. The KM3 net research infrastructures comprises two detector arrays of optical sensors. HARCA, offshore Porto Palo di Capopassero in Sicily, designed to be equipped with two blocks of 115 detector lines, geometrically optimized for TeV, PeV astrophysical neutrinos. Horka, on the other hand, offshore Toulon in France for the detection of jet-scale and atmospheric neutrinos. Each detection line comprises 18 digital optical modules, each of one hosts 31 photomultiplier tubes pointing in all directions and connected by means of an electro-optical cable, so ensuring 4-pi coverage. This is an illustration of kappa internet detector. This figure represents the reconstructed muon trajectory through the red line along which shines the Cherenkov light cone. Vertically, the lines along which the photomultipliers are linked with a complex network along which the particle swarms are visualized. These optical modules are so tightly woven so that the closest one to the muon track are blinded and saturated by the unimaginable brightness and energy load of the event. We are dealing with a few million of a billion of electrovolt. The photomultiplier rates are represented by spheres staked along the direction of the PMT's orientations, colored according to the detection time relative to the first triggered hit, as we can see in the legend, sized to the number of photons detected. This panel of the figure is the zoomed-in view of the optical modules that are close to the first two observed secondary showers in the event, the Blick spheres. Here, light blue spheres represent hits that arrive within -5 to 25 nanoseconds of the expected Cherenkov arrival times. Let's dwell briefly on one direction and energy algorithmically reconstructed with computational simulations. For the simulated reconstructions of KM3-230213A trajectory was used the maximum likelihood algorithm from which this event resulted the best track log likelihood ever. As already anticipated, it happened near horizontally at about 0.6 degree above the horizon and at an azimuth of 259.8 degree with an estimated uncertainty of about 1.5 degree. How can we trace the energy? The best strategy consists of counting the number of PMTs involved in the triggering of the event, net of the incisive interfering factors as the optical background, meaning what the absorption length of light, dark noises, and after pulses. This numbers distribution as function of the moon energy adequately normalized is modeled using Monte Carlo simulations, computational methods based on random and uncorrelated sampling, as granted by the Key-Quare test, which, by densely exploring the entire parametric space, help to build frequentist confidence intervals. The simulations for muon energies of 100, 1000 PeV is represented by these histograms, where the vertical dashed line indicates the number of PMT involved in the kappa M3 event equal to 3672, about 35% of the PMTs active at that time. Unlike dashed histograms, the filled ones include systematic uncertainties. By wavelength with a normal distribution centered at the nominal value of the nuisance parameter and with a more or less 10% uncertainty with an highlighted truncation at the highest energy, probably because the track crossing with the detector's periphery. At the end, the moon energy is estimated of 120 PeV with 90% confidence interval of 35 380 PeV, acting as lower limit on the neutrinos ones. Approximation strictly constrained by some squeezing and brutal assumptions as the inversely quadratic trend of the energy spectrum and the isotropic and equiprobable spread of a hyper energetic flow for a near horizontal event under penalty of being hidden by an overwhelming cloud of atmospheric muons or severely suppressed by Earth interaction. The following illustration shows the position of kappa M3 in the phase plane of the just described number of triggered PMTs in logarithmic scale as function of the cosine of the zenith angle whose boundary outside which the 5 or 1% of the expected yearly rate of atmospheric muons and cosmic neutrinos in arc are contained is marked by solid or dashed lines respectively. These enfeebling events implemented by Monte Carlo approach are selected choosing well reconstructed track, leaning on a log likelihood ratio larger than 500 in order to reach skimming only the 0.02% of all atmospheric moon tracks. The moon rate per year varies with energy increasing by an order of magnitude when from 10 to the power of minus 10 at 100 PeV, the energy decreases by one third. So, because of the amazing kilometer-long crossing, clearly above the 60-kilometer threshold of any atmospheric high-energy moon, and of the drastically decrease above 100 PeV of energy, owing to the quick decay of short-lived hadrons, the atmospheric hypothesis is so discardable. Four hypotheses were so developed: galactic, local universe, transient, and extragalactic origin. No cataloged source, apart from the Orion molecular clouds, was found in the 99% error region of the event. In this figure, indicated by the red star, in support of a galactic origin, comparing it with an extension of the galactic interstellar medium about 10 degrees above and below the galactic plane. By cross matching with the 40 galaxies found at distances up to 100 megaparsec, no optical transient sources as gamma ray burst, tidal disruption events, supernova remnants were recorded. In the hand have been sifted AGN and blazars as extragalactic sources through archival multi-wavelength data whose celestial position is shown of Fermilat for gamma ray, Hirosita for X, and WISE for optical signals. In the surrounding of a central, about 90% energy range, and assuming a flower equipartition, was estimated the steady isotropic flux as energy squared per flower astrophysical flux of KM3 230213A, expressed by the following formula. The CAP-M3 net standalone flux exceeds any other limitations identified so far, probably because the event is an upward fluctuation at the level of 2.2 sigma, equated with an infinitesimal cadence of 1 per 70 year. As the expected number of cosmogenic events is of the order of 1,000, a cosmogenic hypothesis corroborated, or cosmic rays interaction with EBL, or cosmic microwave background, as previously announced. The cosmogenic model is shown in the gray shaded band, whereas the yellow shaded one comprehends transient emitters such as gamma ray burst, TDE, low luminosity blazar Laserte, or flat spectrum radio quasars. The horizontal span of the crosses corresponds to the flux needed to achieve one event in the central 90% neutrino energy range associated with KM3 230213A, whereas the vertical ones, the 1, 2, 3 sigma, felt the Cousin's confidence intervals on this estimate. Perfect. We could pass to the second essay. This is the abstract that I summarize here. The proposed investigation aims to peer into the galactic depths to discover whether KM3 could have originated in the Milky Way, for example, by venturing into the search of potential gas targets as gas-hadron collisions or gamma-ray counterparts as neutrino production channel. But the low fluxes of the galactic diffuse emission at these energies, added to the lack of a nearby potential accelerator, will encourage us to look elsewhere, leaping beyond the edges of the Milky Way into the jaws of the outer universe. To investigate on the role of gas targets on a neutrino's origin, it's used a reliable tracer, carbon monoxide, of which in the next slide we can see the velocity integrated CO map of luminosity temperature from DAMI with the CAP-M3 event overlaid and marked by the red cross surrounded by the red and white circles of 68 and 99% containment reading. The dashed ellipses mark the location of molecular clouds in the ROE that stands for region of interest, with distances from the Earth between about 400 parsec and 2.4 kiloparsec. Zooming near KM3, we can note an intersection of area of gaseous cauldrons as S-Ori filament and monoceros R2 within 99% containment radius of KM3. The first one is at an estimated distance of about 900 parsec with a mass of about 3,000 solar masses, although it's tough to be smaller due to the virial theorem and the local thermodynamical equilibrium. Moon 2, on the other hand, is slightly closer, 3 times severe, and bubbling with stellar activity. This last could be a good candidate, but the average number density of 20 centimeters to the power of -3 is much larger than galactic interstellar medium of zero point 0.2 at the same location. While the hypothesis of an expected neutrino emission from the cloud MON-R2 as an optically thick source in gamma catalyzed by cosmic rays interactions fails due to the flow gap, as well as the hypothesis that MON-R2 acts as a beam dispersing lens from a source behind, because due to the photon scattering it should appear brighter in gamma rays. However, the case in which a beam of accelerated particles from a single nearby source could produce a larger emissivity cannot be excluded. Okay, a big challenge for a potential galactic origin of KM3-230213A is its extremely high energy. The hadronic collisions in interacting cosmic rays indeed need of several hundred of PeV, thus should contribute spectrally to the transitional joints between the ankle and the knee. But just the knee cosmic ray spectrum is caused by a rigidity-dependent cutoff of galactic sources. Furthermore, we must take into account the offset of 11 degrees from the galactic plane and the non-isotropy of gamma ray and neutrino emission by cosmic rays interacting with nuclei. Analyzing briefly the cosmic rays fluxes, so we can highlight that below PeV energies, the atmospheric Moon and anti-Moon neutrino flux dominates over the average diffuse galactic neutrino flux, whereas above some tenths of PeV energies is negligible both in the diffuse interstellar medium and in the clouds here investigated, and anyway well below the KM3 flux due to the steep spectral index of the diffuse cosmic rays, making the association of the KM3 with a galactic diffuse origin unlikely. Let's investigate. Could KM3 derive by supernova remnants? It was recently argued that supernova remnants in massive star clusters might be able to accelerate cosmic rays up to energies of hundreds of PeV, but the particle swarm that unleashes could enjoy a significantly lower energy budget, about of the order of several tens, which is insufficient to explain a neutrino with an energy much larger than the low end of the 90% confidence interval of KM3 of 72 PeV. Furthermore, from the specific supernova remnant catalogs as green, there are none close to KM3. So, supernova remnants are to be a potential source of KM3. What What about stellar clusters? Young stellar clusters can produce a collective wind termination shock where particles can be accelerated. However, in the Kaplan-3 ROE region of interest were not found Wolf-Rayet stars, rare eruptive stars with a luminosity between hundreds of thousands and millions of times that of the Sun, which lose mass at a high rate, about 10 to the power of minus 5 solar masses per year, through very violent and turbulent stellar winds until the hydrogen shell is expelled from the nucleus. Stellar clusters are here displayed with magenta circles, the two ones in gold located within the KM3 event uncertainty region, while the three in red within 5 degrees from the event. Now, the most massive star found is only of about 10 solar mass. Two, all of these clusters have collective wind powers less than 10 to the power of 34 erg by seconds to the minus 1, not enough to give the boost needed to make the cosmic rays shoot up. So, also a scenario of supernova remnant exploding in a massive wind-blowing cluster seems unlikely. And what about X-ray binaries and microquasars? X-ray binaries, whose astonishing power is linked to the drop in the gravitational energy during the mass transfer phase. You can imagine that 10 to the power of 41 positrons are transferred every second from the donor star to the accretor one, stand out in the very high energy X or radio regime. No X-ray binaries or microquasars were found in the region of interest in the Rosetta for X-ray binaries and Combi for microquasars catalogs. And what's more, protons spat out from relativistic jets reach maximum energy of 10 to the power of 16 electron volt. So this hypothesis is unlikely too. Okay, pulsars, on the other hand, with their explosive density due to a solar mass compressed into a few tenths of kilometer and core collapsed into neutron stars, spin very quickly, creating an impressive and enlarged electromagnetic radiation that channels into narrow cones observed as pulses emitted at extremely regular intervals. Now, NHASO had detected many sources above energies of 100 TeV associated with high spin down power pulsars whose maximum achievable energies in units of PeV is written as in the following formula. However, the only two pulsars found within a distance less than 5 degrees, whose names can we read here, have an energy loss rate far too low to reach even PEV energies requested. 2. If the cone of open fields lying around a pulsar's magnetic pole doesn't point towards the Earth, no pulsed emission can be detected. 3. A powerful pulsar is expected to produce a bright white nebula visible in gamma rays that is believed to be of leptonic origin, but an hadronic component is not excluded. In consideration of all, no known pulsar can be a potential cosmic ray accelerator for kappa M3. Okay, to finish, neutrino formation via hadronic collisions or photomeson production inevitably leads to the creation of gamma rays, which even strong stellar ultraviolet radiation can't absorb. And furthermore, even if the neutrino could have been produced at the outer edge of the Milky Way at a galactic plane and a galactic radius of 2.4 kiloparsec, only 3.4% of the gamma ray emission is lost. Nevertheless, Fermat observes only two gamma ray sources within the ROHI, from tens of MeV up to several hundreds of JeV, too low for the event. These are the sources of a non-type that Fermi has found through a power law distribution with an index equal to minus 2.5 till 100 TeV of energy and minus 2 for highest energy at the diffuse shock acceleration, being too low compared to expectations and with a flux more than 3 orders of magnitude below. One can safely neglect the absorption by the large-scale fields. In conclusion, it's therefore highly unlikely that a strong hidden galactic source have produced kappa M3-230213A, and an extragalactic origin is much more likely. I explain you the third and last essay at how you can see. The focus of this essay is to investigate whether what was discovered from the neutrino ice cube 170922A can be repeated for kappa M3. That is this originated from a blazar? From multi-wavelength and time-domain analysis, 17 potential blazars were found in the 99% confidence region, 10 of which show strong radio emission on the parsec and subparsec scales, indicating strong jet beaming effects. This the abstract that I explain in the following. First of all, what are blazars? A subclass of about 5% of active galactic nuclei, so-called AGN, with highly collimated jets pointing almost directly toward Earth, which emit across the whole of electromagnetic spectrum from radio frequencies to very high energy gamma rays greater than 100 JeV. Exactly, their spectrum combine a compact flat radio spectrum with an continual broad and non-thermal radio one with the peculiar double amp. Blazar's emission occurred through two kinds of processes: leptonic, which branches out into synchrotron emission of accelerated electrons and inverse Compton scattering, and leptohadronic one, divided into photopion and Bethe-Heitler photo pair production, in which accelerated and ultra-relativistic ions interact with photons or protons, producing neutral pions, decaying into high-energy gamma rays, or charged pions, decaying into muons and neutrinos, are displayed in this image. Or, at the end, could produce electron pairs of matter and matter nature, whose tangent we can see in this log graph, which is placed next to a table with indication of threshold cross sections and inelasticity data for photopair or pion. Particularly suggestive is this image of a blazar cascades down to lower energies depending on emission density from a radius of 0 to Schwarzschild radii, with a representation of all kinds of emission and effects as shock and superluminal knock, or the formation of helical magnetic fields. What are the conditions required for a blazar to be the source of a muon neutrino with energy between 72 PeV to 2600 PeV? Let's look for a very brief mathematical support. Each proton or photon hit by ultra-relativistic ions must have a minimum energy equal to 20 times that of the neutrino produced, which varies between 1.5 electron volt and 300, the highest observed for cosmic rays arising from AGN's jets. So, knowing the effective area in Arca of about 400 meters squared, the luminosity distance of about 7 gigaparsec for located redshift for 1, and assuming a beaming factor of 1000 for a focused jet within 4 degrees, we can calculate the source luminosity and minimum jet power through the 1 and 2 formulas, discovering a typical blazar brightness of 10 to the power of 45 in a rate of 75 years. By adding an impedance of about 30 ohms in the potential crossing of the formula tree, the minimum jet power is readjusted to extent of 10 to the power of 42 erg by seconds to the minus 1, which is clearly lower than the 300 electron volt. So the connection between KM3 and blazars, or highly variable and fast electromagnetic flares, is likely. The technique used is a multi-wavelength investigation aimed to characterize the electromagnetic blazar's properties and reduce possible degeneracy through detection of brightness spectrum, but above all, temporal correlation between the neutrino and blazar's flaring time, as the next simulation shows in a concise and exhaustive manner, in which is cross-matched the neutrino's time cruise and the blazar's ignition. Thanks to this complex hyperspectral analysis, very precise criteria have been defined for capturing the highly luminous AGN jets with strong beaming. A bright parsec scale radio emission, a flat radio spectrum due to synchrotron opacity, a spectral index greater than minus 0.5, a core brightness temperature greater than 1010 Kelvin at either 5 and 8 gigahertz, and a 99% localization area. In this circular diagram, the 17 blazars found are listed and localized with four models based on X radio and infrared cross-matching, a parsec scale flux density over a threshold of 100 millijansky at 8 GHz, the 5P zeta cut model, and the Fermi-Lat one. But only three sources were found that we can see hashtag below are compatible with spectroscopic and redshift analysis and are classified as flat spectrum radio quasars, which are optically violent variable quasar based on the presence of broad and highly variable emission lines in their optical spectra. I'll introduce you to the three sources very quickly. The first one is 0605085, the brightest radio source on a parsec scale emission with an image, with an intense, gamma ray activity around the kappa M3 arrival, indicating a high degree of relativistic beaming, of which I report the animation created on the Moyev website relating to the polarization for the first one and the intensity for the second. This is Fermi-Lat light curve in Julian date, showing a gamma ray flare peaking just some months before KM3 event, perhaps due to its proximity to a foreground star. The second source is PMNJ 06060724, recorded independently by two radio telescopes in California and Caracacia, presents dense uniform radio light curves, which peaks at 15 GHz. It's the strongest temporal correlated kappa M3 arrival, only 5 days of observed time delay of the radio peak. This correlation was studied through test statistic map defined by the double logarithm of the ratio between the likelihood with or without surge, and with the fitted narrowing iteratively the three parameters until their convergence, obtained at a statistical significance of at least 4 sigma compared to the maximum threshold of radio flares. Just through test statistic factor resulted a PMN values of t s equal to 5 days, leading to a p-value of only 0.26, indicating a 1 in 318 purely by random chance to observe a time difference of 5 days. The last one is MRC 0614083, a valuable tracer of hadronic components thanks to its X-ray flares. It's the closest object located at 0.6 degree away from the best fit neutrino position. This graph is an evaluation of the chance probability of finding within 3 degrees a blazar with radio light curves and a strong time correlation at the edge of overall monitoring area, less or more 10 degrees from the galactic plane, while KM3 net event is relatively close to the galactic plane, remember 11 degrees. In conclusion, time variability exploration across multiple wavelengths leads to a close coincidence only with the major radio flare in PMNJ 0606 with its probability of 0.26%. However, the absence of strong and unequivocal correlation of hadronic processes across different electromagnetic bands. However, improvements in the calibration of the KM3 net the telescope are expected to decrease the systematic uncertainties in the directional reconstruction of KM3. to reduce the degeneracy in the identification of possible counterparts. So, a huge question mark remains over the neutrino blazar correlation. Okay, dear friends, thanks for your attention. See you soon. Bye.